welcome to another WJEC A level physics question. This time is question 6 from June 2017's Unit 4, which was A2, but this work on wave-particle duality you'll now find in Unit 2. First part of the question, we're told that light of wavelength 635 nanometers is emitted from a laser. We've got to determine the energy of a single photon in the beam. And here we can simply use E equals hc over lambda, but bear in mind that equation is not in the WJEC data book, so it's one to learn. H is Planck's constant, 6.63 times 10 to the minus 34. C is the speed of light, 3 times 10 to the 8. And lambda is the wavelength, 635 nanometers. And the mistake I've seen people make here is to forget that nanometers is 10 to the minus 9. So that needs to be put in place. Putting those numbers into a calculator gives us 3.13 times 10 to the minus 19 joules. And I've stored that answer in a memory on my calculator because we're going to use it again later, and it just saves a little bit of time and avoids rounding errors. For the second part of the question, we've got to find the momentum of a photon. And the momentum of a photon is given by P equals h over lambda. H again, 6.63 times 10 to the minus 34. Lambda, 635 nanometers. And this will give us an answer of 1.04 times 10 to the minus 27 kilogram meters per second, or possibly Newton seconds. For the last part of the question, a laser beam is incident normally on an area of 2 times 10 to the minus 6 meters squared, where it's totally absorbed. And if the output power of the laser is 3 milliwatts, we've got to determine the pressure exerted by the light on this area. Well, this output power, 3 milliwatts, is 3 joules per second. And we know that each photon has an energy of 3.13 times 10 to the minus 19 joules. So we can find our number of photons per second, I'm going to call it n, by taking 3 milliwatts and dividing it by the 3.13 times 10 to the minus 19, the energy of each individual photon. So putting those into a calculator, we end up with 9.58 times 10 to the 15 per second. Each of those photons has a momentum of 1.04 times 10 to the minus 27 kilogram meters per second, so we can find the total momentum of the photons per second, and this will actually be equal to the total momentum change per second, because the photons are going to go from having a momentum of 1.04 times 10 to the minus 27 down to 0 because they're absorbed. So the total change of momentum per second is going to be that 9.58 times 10 to the 15 multiplied by the momentum of each photon. If we put those into the calculator, we get an exact answer of 1 times 10 to the minus 11. Now, if we realise that kilogram meters per second, that's force, because Newton's second law tells us that the total rate of change of momentum, or the total change of momentum per second, is force. So in other words, what we've just worked out is that the force exerted on the area is 1.0 times 10 to the minus 11 newtons. Finally, we can calculate the pressure from force over area. So we got 1 times 10 to the minus 11 over 2 times 10 to the minus 6. That's going to give us an answer of 5 times 10 to the minus 6 newtons per meter squared, or pascals, whichever unit you prefer. So thank you very much for listening. Please remember to like and subscribe, and feel free to leave any comments. Goodbye.